welcome to this review of the 2019 WJEC Physics Double Award Physics paper, the Foundation tier. Going to go through some of the common things with these questions. This should enable you to mark your own if you've gone through this paper, and to then I'll discuss about reviewing it afterwards. Okay, so got here two cameras. Can try and address one camera when I'm doing some talking about stuff, and obviously you got the one down in front of me where you can see the paper that we're working on. So let's have a look. So first things first, on the front page, it's always worthwhile reading the front page. Question 5 is our Curie, and we're doing all the questions. Use space is provided. Page 2 is the equation page. Very useful, definitely worthwhile getting to know this. Especially things like the prefixes and the equations here in both words and symbols. Okay, question 1. So question 1 is asking us to find out about density. So the first part, 1A, so it's important to read, have a look at this top information. And there we go. So complete the table below. So the first question is asking us to complete this table. So the mass of the bone we get from there, 32.0 grams. The volume of the bone, well, volume of the bone, before the bone it was at 60. After the bone it's gone up to 65, 66, 67, 68. So the bone has caused that increase. So the difference between them must be the volume of the bone, 8 centimeters cubed. Now density, using an equation from page 2, we find that density is mass divided by volume. So we do our mass divided by our volume to give us 4 grams per centimeters cubed. Now in terms of the marks, because this is our first, well, it was 1 mark for that, 1 mark for that, 1 mark for correctly using the equation. You do get error carried forward, so if you've got 32 or 8 wrong, you can get that mark there still, and then a mark for 4. The common mistake people used, if you use 68 here and you get an answer of 0.47, you can still get both marks because you've still used your information from the question above. Explain in terms of particles why bone has greater density than water. Okay, so this is worth 2 marks. We're expecting 2 points. So if we think about solids compared to liquids, solid particles are arranged all close together. So therefore, in any given volume, we can get more of them in. So that's what we're going to write down. Particles in the bone are closer, or better, are more tightly packed. So there is more mass in the same volume. And it's 1 mark for each of those lines. So 1 mark for that, 1 mark for that. Okay, question 2 then. Now, if you haven't seen on YouTube yet, our video, which actually details quite a lot of the stuff on this, I'll make sure there's a card that appears somewhere that has got it. So shows the main parts. So this shows main parts of a thermal power station using coal. Complete the diagrams. We've got to put a word in here: furnace, steam, turbine. And then we go on to the next bit then. So the furnace is our chemical energy to heat energy. We're burning stuff. We're releasing the heat energy in the fuel to make, changing the chemical energy into heat energy. And our generator takes kinetic energy from the turbine, the clues in this arrow showing that spinning shaft, into our generator. Okay, values to the power stations. We input that. We have our heat energy, we have our electrical energy. Use this information to calculate the efficiency. So efficiency is useful divided by total. Now, power stations, the useful energy is the electricity. The total is this number here, the energy supplied. So we put them in. Times by 100, because it's asking for percentage efficiency, and that gives us 30%. 2 marks here. 1 is for putting the correct equation. Let's get the red. 1 for getting the 30. Likewise here, the 2 marks is just 1 for each arrow. So there's the answer. Useful energy 4,500. Input energy 1,500. Oh, sorry, 15,000. Times by 100 to get our percentage. Question 3. A ripple tank is used to demonstrate water waves as they travel from deep water to shallow water. The results are shown in the diagram below. Water waves change direction at the boundary between deep and shallow water. State the name of this effect. So if they're changing direction, the only thing we have is refraction. Okay, so waves, when they change in direction, we call that refraction. So we want to tick 2 correct statements that describes the frequency of the waves is higher in shallow water. Now, frequency doesn't change. You can't lose waves, so the frequency, how many arrive in per second, cannot change. The amplitude of the waves is the same in deep and shallow water. Now, we can't tell anything about amplitude from this diagram. This diagram is just showing us where the tops of those waves would be. So let's have a look. The wave speed is less in shallow water. Yes, you've done that practical. You should have found that as the amount of water in a tray got less, the waves travelled slower and slower. The wavelength decreases. Well, the wavelength here is actually the gap between these wave fronts. So therefore, yes, the wavelength also decreases. 2 marks, 1 for each of these points. In deep water, the waves have a wavelength. Let's just see when we change the focus. Of 3 centimeters and a frequency of 5 hertz. Use this information in an equation from page 2 to calculate the wave speed. Okay, so we have been given wavelength. We have been given frequency, so we're selecting this equation. We're just multiplying the 2. Now, the units they've asked for are centimeters per second, so we can just do 3 times 5 is 15 centimeters per second, because this is in centimeters and hertz is the same as per second. So that gives us our correct units straight away. 2 marks, 1 for the substitution, 1 for the answer. Okay, question 4. So the government intends to phase out the use of petrol and diesel cars by 2040 and encourage us all to switch to electrical vehicles. Here they've made up to the Voltsa and the Ampera, and they're giving some information about them. So it's important to read through this information when you do this question yourself. For now, I'm not going to bother because we're trying to get to our answers. Especially as this question, use the information in the table. Eric travels 110 kilometers each day. He is concerned about his carbon footprint. Why should he choose the Voltsa rather than the Ampera? Well, if you look, the amount of carbon dioxide the Voltsa produces is 0. So it's no CO2. Don't want less carbon? It's no, there is none. Calculate the mass of the CO2 produced if the Ampera is driven 250 kilometers. Well, if you look, grams per 100 kilometers is 700 for the Ampera. Well, we are doing 250. So 250 in hundreds is 2.5. So we're just going to do 7,000 times by 2.5 to get 17,500 grams. In terms of the marks here, it is again 1 mark for correctly using 7,000. As long as you've written 7,000 in that bit of the question, you will get that mark. And the second mark is for getting the right answer. If you've got 1.75, somewhere written down 1.75, 1,750, something like that, you can have 1 mark. Okay, for part B, the Voltzer can be fully charged in 6 hours using a 4 kilowatt charger. When 1 kilowatt hour of electricity is generated, produces 0.4 kilograms of carbon dioxide. Calculate how much CO2 is produced to fully charge the Voltzer. So we do 6 hours at 4 kilowatts. We do 6 times 4 to give us 24 kilowatt hours of electricity used. And then we do 24 times 0.4 to give us an answer of 9.6 kilograms. Because each one of our 24 releases 0.4, so we get 9.6. Ian says that the data, CO2 data for the Voltzer is misleading. Explain why. Well, it says no CO2 is produced when driving. But where's that electricity come from? We've already worked out that we produce 9.6 kilograms of CO2 when we charge it. So our table states no CO2, but some is produced during charging. Okay, so the important bit here is table states no, but we do have some from the power station. So those are the 2 marks. One for saying no, table says no. The second is for realizing there must be some from charging that's not being included. Let's put that down. That is not included. Whoops, realized you can't see that answer. There's that answer there. So table states no CO2, but some is produced during charging, and that's not included. Okay, over the page then. Ian drives 600 kilometers every week. He is not going to buy the more expensive Voltzer since it will not save him money to run compared to his petrol car. Explain whether you agree with Ian. Okay. So, our petrol car then, if we look back at our table, our petrol car can travel 600 kilometers on 1 tank of fuel. The volume of petrol used, let's have a look. The volume of petrol used in litres per 100 kilometers is 7. So each 100 kilometers you drive, it uses 7 litres of fuel. So we in 600 kilometers, we're going to do 6 times 7, which is 42 litres used. So now how many litres of fuel we've used? And each litre of fuel is 120. So the cost is going to be 42 times 120, which is 5,040 pence. We're in pence here still. Careful of that. If you put pounds in that, if you do 5,040 pounds, you're going to get that answer wrong. Okay, the cost of using the Voltzer. The cost of one full, it does 150 kilometers on 1 charge and 264 pence per charge. So, to do 600 kilometers, we're going to need 4 charges. So 4 times 264 is 1056 pence. So, in terms of cost to run, we disagree, as Voltzer is, well, nearly 4,000 pence cheaper. Now, in terms of the marks here, you don't actually get a mark for saying your conclusion. What you get the marks for is for the 5,040 and the 1,056. However, if you don't put this in, the conclusion bit, you don't get both marks, you'll only get one. So get the right numbers and conclusion, 2 marks. Get one of the numbers, or get both numbers and no conclusion, only 1 mark. So bear that in mind. Okay, question 5. QER question, quality of extended response. Now with these, remember the marking scheme is a little bit tricky. It's not just say something, get a mark. You've got to look at which band you would sit in. And it's basically, if you've got everything, so you've got all the named parts, all the similarities, all the differences correctly identified, then you're going to be in that top band, and the language will decide what you get in that band. If you've got 2 of the areas, then you're going to be in the middle band. If you've only got 1 of the areas, you're going to be in the bottom band. So, in terms of how would I go about this answer? Well, in terms of quality of written communication, doesn't always mean you've got to work in perfect prose. For this sort of answer, I would probably, I want to name the different regions, I want similar, and I want their differences. So, to be honest, bullet points for quite a lot of this will do. So we could have different region, like so, and we could just list them. So we've got 7, and we will start with radio waves. Then we got our microwaves. Then we have infrared. Then visible light. Then we have ultraviolet. Then we have our X-rays, and then I'll write it out properly, gamma rays. 1, 2, 3, 4, 5, 6, 7. There we are. There's our 7 different regions. So we've already done one area really well. So we're 1 to 2 marks. We then want, now what it's not asking for is uses. It's asking for similarities. It's asking for differences. So again, I would probably just go put a title here. Similarities, and I would list them. So they're transverse waves, they transfer energy, and the key one, they travel at the same speed in a vacuum. And then perhaps I'll put my differences here. So differences, well, we could in fact put some information on here. We could have increasing frequency, decreasing wavelength. So there's 2 differences I've listed straight away. You could say different uses. So their uses are different. You could also say X-rays, UV, X-rays, and gamma rays are ionizing. Now you might think, hang on a minute, that's not like continuous prose. Am I going to lose marks? Well, it says there is sustained line of reasoning which is coherent, relevant, substantiated, and logically structured. To me, that is all of them. You might lose 1 mark. You'd get 5 out of the 6. They might deduct you 1 because it's not continuous prose. But personally, I'd have given that answer 6. It's got everything in it, and it's in quite a nice, it's laid out in a nice way for this type of answer. Now, other QER questions do require a more of a paragraph, but this one, definitely, that would be sufficient for that question. Okay, a thermistor then. So question 6. We're now on to looking at electricity. Thermistor, type of resistor. So you got that top bit. So complete the diagram. So thermistor. So we want a thermistor. We want to be able to the voltage. We want to be able to measure the current. So a thermistor is like so. It's a rectangle with a line through it. Ammeters always go in series. Voltmeters always go in parallel. Now in terms of the marks here, 3 marks, it's basically a mark for each symbol being in the correct place. Okay, students place the thermometer in water, plot the data on the grid below and draw a suitable line. So we've asked to plot resistance and temperature. So we're plotting these two. All right, so been over, oh yeah, you've seen some graph stuff. No, you haven't seen graph stuff. That was you now. Excuse me on that. Right, so going over graphs. 20, 1200. 40, 5,400. So we've got 1, 2, 3, 4, 5. So each one of them is 2. 60, 2,500. 80, 1,400. 100 is 600. Now, a couple of common common pitfalls that students fall in here is 2,500, for example. People would put it smack bang in the middle, but take care on 2,500. Take care on these axes. This goes from 2,000 to 4,000, not 2,000 to 3,000. So it's not smack bang in the middle. It's going to be a quarter of the way up, 2.5 boxes. So I've got this. I now need to draw a suitable line. Now what you will notice is I've drawn the points in pencil. In pen. No harm drawing the points in pen if you're confident. They've got to be within one small square of where they should be, which all of them are. Now in terms of the line, me being left-handed, this line goes like this, so I'm going to turn my page upside down because my hand naturally wants to sweep from bottom right to top left. If you're right-handed, you probably want to turn the paper that way so that you can go like that. The line, however, I am going to do in pencil in case I make a mistake, so I can do it again. I have a few practice goes, and then I go for it. Now, key thing with the line is it should be within one small square of each of these points. So I would just about get it. So I would get all 3 marks. 2 marks for the correct points. 1 mark for the line. If you got 1 point out of place, you get 1 mark and 1 mark for your line. And there we go. The other key thing, make sure your pencil's nice and sharp when you do these. Describe what happens to the resistance of the thermistor as the temperature increases. Now, again, plug in the YouTube, have a look at the video I've done on drawing graphs, go through all these different relationships. 2 marks, 1 mark for saying what happens to the 2 variables, second one is for talking about the gradient. So, increased temperature, what happens to the resistance? So, the resistance decreases. Now, because of the way this question is asked, we can just write decreases. What happens to the decreases? It decreases. We know what we're talking about. The second mark is for saying at decreasing rate. So 1 mark for saying decreases, 1 mark for decreasing rate. How do we know it's a decreasing rate? Because if we follow this with our pen or our ruler, that rate is, the line is getting less and less steep as we go on. Use your graph to find resistance of 50 degrees Celsius. So your graph, you come up from 50, where it crosses is there. They want to see some evidence of you using 50. In fact, it's not quite 4,000, it's just below 4,000. In fact, it's halfway. So I'm going to say mine is 3,900. You're allowed here, if you look at the mark scheme, anywhere between 3,600 to 3,900. It doesn't quite go to 4,000. But it is your graph. So if you do get out of that range, as long as it's what's on your graph, that's fine. Use an equation from page 2 to calculate the current. So I've got resistance and voltage is here. So I've got resistance, I've got voltage. I want to find current. So it's this equation at the top. So current, or I, is voltage divided by resistance. In this case, 12 divided by 3,900, because that's what I've used. That gives me an answer of 0.0031. In terms of the marks, it's worth 3 marks. So it's 1 for selecting the right equation, 1 for putting in your answer of 3,900, and 1 for 31. Okay, a temperature sensor needs to vary in resistance by at least 3,600 as the temperature changes from 40 to 80 degrees Celsius. Use your results from the experiment to explain whether the thermistor used by the students is suitable. So if we look at 40 degrees, we get 5,400. If we look at 80 degrees, we've got 1,400. Now the difference between these is 4,000. So we can write this in our answer that we've got 40 degrees Celsius, I'll just use the right colour pen, equals 5,400. 80 degrees Celsius is 1,400. So the difference, or the change, delta means change, is 4,000. So, suitable. Right, mark scheme here. 1 mark for doing the sum. 1 mark for reading the right values. But again, you only get the 2 marks if you have said it's suitable. So bear that in mind. You could have done the hard work, but because you didn't say, yeah, it's suitable, you would not get the 2nd mark. That's how they roll in these. Okay. Question 7 then. Now this, guys, is the common question between higher and foundation. So this question actually appears on both papers. So lots of information. Read through it all before you answer this question. Really, really important that you do that because we're going to need it for this for the rest of this question. Information on the cost of televisions is given. So use the information from the labels to tick. So these labels, I know in my class I don't necessarily go through these labels in too much detail because they're really common sense. Everything is there. So anything electrical that you buy will come with one of these labels. They give the energy rating in a bracket. They're going to tell you how many kilowatts per year, how many watts the TV, so that's how much electricity it uses per year. The watts tell us how many watts it uses, so that's the power, so that's basically how many joules of energy it's going to use per second. Then it gives us the screen size. Okay, so we're going through these. Television 1 uses less energy per second than television 2. So television 1 is 32 watts, television 2 is 78 watts. Remember, that's energy per second. So yes, television 1 does indeed use less energy. Let's go back to our black pen. So that's correct. The largest televisions always use the most energy. So the largest television is here is 163 centimeters. That's 153. Then we have 123, 124 watts. But then we've got our 39 is 78. So that doesn't work because they don't, the screen size and the wattage is not in a same ratio, or they're not in the same order. The cost of television 2 is 1.5 that of 3. The cost of television 2 is not, it's the other way around, that one. More expensive televisions always use less energy. So the most expensive television is television 3, And in fact, that uses the most energy, so that's not correct. Television 3 uses 40 units more than television 4. Yeah, the difference between those two numbers is 40, so that's fine. Televisions with the same energy rating don't always have the same power. And that's correct, because we've got a 32 watt telly, which is an A, and we've got a 153 watt telly, which is also an A, so that's also correct. 3 marks, 1 for each of the boxes. It is claimed that power is proportional to screen size. So proportional just means as one changes, the other changes. Use data from television 1 and television 2 to determine if this claim is true. Now, if they were proportional, we would have the same ratio in both of these between power and screen size. So that's the sum we're going to do. So we'll do 139 divided by 69. Yeah, so that's the screen size ratio is 2.01. And then we have the power ratio, which would be 78 divided by 32 is 2.44. So ratios not the same. So so claim is untrue. Now, if you look in the mark scheme, there's a variety of ways you could do this. You could compare the ratio. You could do the screen size divided by the power for each one. You would see that's not right, and that's probably the only other way that's a sensible way of doing it. In this one, what we've done is this is our screens, this is our power, and if this claim was true, those two numbers would be the same. They'd have the same ratio. Okay, so we're now going to use the equation. Time in hours is units used in kilowatt hours divided by power in kilowatts. And the data from the energy label to calculate how many hours the label suggests television 2 is used. So television 2 uses 108 kilowatts and its power is 78 watts. So we've got to be careful here. We've got kilowatt hours on the top, we've got watts on the bottom. So we need to convert our watts into our watts into kilowatts. So that's 78 divided by 1,000. So that's the sum we're going to do. Now, when we do this, we get 1,384.6 hours. Now, you could have rounded that to 1,400 hours. That would be acceptable. To 1,380 hours, that would also be acceptable. 1,385 hours, as long as it's rounded correctly, that's fine for this answer. Now, quite a lot of you, I bet, have got an answer here of like 1.3 hours or 1.4 hours. Think about it. How many hours a day do you watch a telly? You know, I bet it's more than 1.5 to 1.5 hours a day, let alone in a whole year. So this is where a little bit of common sense will immediately, if you'd have done 108 divided by 78 and you get 1.4 as your answer, or 1.3846, and go for a whole year, less than 2 hours, you couldn't even watch a film. You know, you couldn't even watch a football match, 90 minutes, an hour and a half, 1.5 hours. So take that in mind when you're doing these sort of questions. Use the equation from page 2 to calculate the cost of it for 1 year if 1 unit costs 16 pence. So we want cost, so it's units used times cost per unit. So the units used is 108 times by 16, which gives us an answer of 1728 pence. This is in pence, that's in pence. Our question wants it in pounds. So to put that into pounds, we divide by 100, £17.28. So take care. They like doing this, converting from pounds to pence to trick you. Okay, so the expected lifespan of a TV is 10 years. Sarah concludes that it will be more cost effective to buy and run television 2 for 10 years, but Sarah disagrees and claims that TV4 will be cheaper. Use the data to determine who is right. Okay, so we're talking over 10 years. So if we look, the purchase cost of both, TV2 is 1,000, TV4 is 800. We've said in the previous question that every year TV2 costs us £17.20 to run. So over 10 years, that's going to be £172.80 in terms of running costs. So this gives us the total cost for TV2 is £1,172.80. Now TV4, its power is 172, its energy in the year is 172 units, times 0.16, times by 10 for the 10 years, and this gives us a total cost, put the decimal place back in the right place, of £275.20. So if we add up this number, this tells us that for TV4, the total cost is £1,075.20. So Sarah is correct. Now, in terms of the marks here, it's worth 3 marks. So the marks, doing it this way, you would get 1 mark for somewhere having the £172.80. Your second mark is going to be somewhere having TV4 correctly calculated. Is for doing the £275.20. Third mark is for getting the total cost of TV4. However, you can only get, again, this third mark if you've written something about Sarah in there. If you've not said that thing about Sarah, you're not going to get the question. Other than to save money, why should consumers be encouraged to choose appliances that use less energy? Well, if we're using less electricity, we've just got to use fewer power stations. And if we're using less power stations, we reduce CO2 emissions. So that's why we want to reduce our energy uses, is because we just got to then generate less. Okay, so thank you for watching this. What I want you to do now is on the email where where I've sent a link out with this video, there will be a link to a Microsoft form. So what I would like you to do is to go through and fill out the form. So what you will see is the following. Let's just bring up this. So this is what you'll see. Let's just change the order so you can still see me. So this is what you'll see. So what I want you to do is to go through for each question, whether you've got, what marks you got on each question. Now there's no box for no, so if you didn't get any marks, just leave it blank. And a couple of the questions, let's see if I can find one. Unfortunately in this system, I can't give just one option, just one. So where a question was out of 1, it's still going to say 1 and 2. Yes, I know that. Just give yourself 1. Then what will happen is when you see your response, in fact, I'm going to just make a change here. Question 1, above question 1 is going to have your name and your email address so that I can reply with your grades. Once you've done all of this, there's going to be a box at the end which will ask you to rate, to give again 2 stars and a wish. So 2 good things you did in this and 1 thing you'd like to improve. Okay guys, so thanks for watching this review of the foundation tier paper.